Yeah, okay, so I'd like to thank Sarah and Peter for inviting me to come here again. It's great to be back. This project with James Maynard has quite a few IAS connections. Not only did we make a lot of progress these last couple of weeks, but the project started when he was visiting IAS 5 years ago, came to Urbana, and that's when he suggested to me to start working on this project. It's also related to an old paper of mine that I wrote in 2005. And that paper also started here when I visited, I think around 2000, and Enrico advertised one of his papers to me. So quite a few connections. The basic problem is we take a finite set and we want to locate or count the primes in that set. And one of the basic tools that has been developed over the last century for doing this is called the Sieve. So there's an exact formula based on the idea of, let's say, going back essentially to Eratosthenes, that if the set is contained in 1 through x, you detect the primes by removing elements divisible by a prime less than the square root of x. So if we want to count, say, the elements of A that have no prime factor less than some quantity y, there's an exact formula for this. Mobius function, and where AD is the set of elements in A divisible by D. So from some point of view, this solves the problem, but not really, because this sum has far too many summands. It's not very practical. So the idea of the sieve is to replace this big sum with a much smaller sum. At the expense of replacing equality with some kind of approximate equality. And the number of summands here is essentially exponential in y, where this is polynomial in y. So it's a much more tractable problem. And depending on the information we have about A sub D, that determines, so to say, the quality. Okay, so the quality is determined by what we know about A sub D. Is it how well behaved it is? And the basic hypothesis is that it's well behaved for, let's say, most D up to some power of X. Obviously, the larger the gamma is, the better off we are. Okay, I'm thinking of A, let's say, in the interval 1x. And the best possible we could have here is gamma being close to 1. Maybe not equal 1, but maybe 1 minus little o1. So that's the best possible distribution we could have in arithmetic progressions. And a basic question is that enough to detect primes in the sequence? And many of you know there's a famous result of Selberg that says the answer is no. So gamma equals 1 minus little 1 is not enough to detect primes. And the set that does that is the set that has an even number of prime factors. Now, by the prime number theorem, this set is well behaved up to x to the 1 minus little o1. So it has best possible distribution. And evidently it has no primes. So the hope of sieve theory that this kind of procedure would produce or allow us to detect and count primes has spectacularly failed. However, has been well known since the 1930s, work of Vinogradov. If one adds another hypothesis on to the set A, it may be possible to detect primes. More generally, we can consider replacing our set A with a non-negative weight function, which you can think of as the indicator function of a set, or possibly a multiple of the indicator function of a set. In a set, in the case, say A is a sparse set. So if A is very sparse, Wn would be either 0 or some very large constant. I'm going to normalize things so that the weight function has average value 1. Now, this is a simplification. In real life. These statements would be slightly different, but I just want to give you a flavor. So the statement up here that AD is well behaved translates into something called the type 1 bound. The new information, which is a bilinear condition, is the type 2 bound. And so this is a bilinear kind of convolution looking inequality. And it's the crucial part is that this is true uniformly for all complex sequences alpha n and beta m, which are bounded. Okay, so it's a very strong condition. And it's known that you can get primes under certain circumstances. So what are the two main problems in the field? The first I'll call hypothesis A, theta nu gamma. So there are these three exponents, gamma, theta, and nu, which govern the strength of these two hypotheses. So this hypothesis says for every weight function satisfying 1 and 2, we have the expected asymptotic for the sequence on primes. Okay, so this is what we're after, is to understand the sequence on primes. And there are some situations where we don't expect an asymptotic, and more generally, we can define a constant C theta nu gamma, which is an infimum of all constants C, such that this sum is at least C minus little o1 x for every Wn satisfying 1 and 2. Okay, so maybe we're not getting an asymptotic, maybe we're getting a lower bound, which is half of what we expect, or 1/4 of what we expect. And what's the infimum over all such constants? All right.
So
now,
what you're developing is a sublimit theory for type 1 and type 2 sums. Is that what it's basically? I mean, the type 1 sum is very much studied.
yes, yes.
And are you trying to understand the sublimits for type 2? Is that the
Yes.
type 1 and type 2?
And type 2, yes.
To combine, yeah.
Yeah.
So, okay, good.
Now, you put new equals 0, and this disappears, and we're back in the small sieve type 1 only world. Yeah. So let's put this higher, and we'll leave it there. So the two main problems are, okay, I guess I should have went. The main problem here is, when is this constant positive? Under which triples gamma nu theta do we have a positive C? Now, there have been some successes with this method, especially in the last 2 or 3 decades. So I'll write down a few of these here. And so first, a famous one. Now I'm ignoring some epsilonic factors here. So with gamma being 3/4 by itself, not enough to detect primes, but with this additional bilinear condition in the interval 1/4, 3/4, Friedlander and Ibanez were able to prove that there are infinitely many primes in the form square plus the 4th power. And so and moreover, their methods gave an asymptotic formula for this. So this was tantamount to solving hypothesis A 1/4, 1/2, 3/4. Okay, that was one example. Another one I want to mention is work of my co-author, James Maynard, on primes with missing digits. Now you can see that the type 1 information is strictly weaker and the type 2 information is a lot weaker. He did not obtain an asymptotic formula for the number of such primes, but he obtained a lower bound of the expected order. And this was tantamount to showing that C of 0.649, 0.36, 0.625 was positive. So with those parameters, he essentially showed this quantity here. Again, he wasn't concerned with the value of it, just once it was positive, that was good enough. Now, dropping gamma a little bit more, and with a different sort of type 2 range, in older work of Duke, Friedlander, and Ibanez, they were studying the distribution of quadratic congruences mod P. The idea is we fix A, vary P, and understand how the numbers, how the solutions behave. So let's say counting how many of these are in some two multiples of P, where alpha and beta and A are fixed, and we vary P, and we want to say how many primes have this property. So they developed a sieve with this level of distribution and this range of the type 2 bounds, and obtained an asymptotic. Okay, so again, it's possible to have an asymptotic even with that small a gamma, and very closely related was a paper Sarnak and Ubis, who were studying certain dynamical systems at prime times. And so does the behavior match the behavior at all times in the distribution sense? So notice that this is 1/5, so weaker type 2. They did not obtain an asymptotic, but they did obtain a lower bound of the expected order. So C of 1/2, let's see, beta is 0, 1/5. Greater than 0. Yeah. So this is just a small sampling. There are many, many other examples in the literature. Now, some of the techniques that are used to prove these are, there are these famous sort of prime decomposition identities due to Linnick, Vaughan, Heath Brown, and others. And these are used and very successful in showing asymptotic formulas. And
That's a picture of some more concrete. Like if I was trying to show some gamma theta and you couldn't work, what kind of set would I?
okay, we don't have a grand picture of that. That's part of what we're trying to study here.
Okay.
As far as I know, before our work, there was no example of a theta nu gamma for which it had been actually proved that the constant was 0.
Yeah, sublimits are.
Yeah, it's
But one thing that I like, there is something very natural about distribution 1/2. Like even understanding the sublimit for 1/2 on the second type, because the 1/2 is what you usually get from Urbana-Champaign or something.
yeah, and I mean you can think of von Vinogradov and
Right, they always 1/2. That's kind of an important parameter on the.
yeah. So I'm going to comment more about some,
You don't agree.
and I'm going to talk about what happens when gamma is less than so. Yes, so there's the.
Yeah. Or you can make gamma and still do that.
Yeah, so I mentioned these identities in the case where one doesn't expect an asymptotic and you just want to prove a lower bound. There are methods based on Buchstabe iteration, which are sometimes commonly called Harman's sieve. So I'm not really going to talk about what that is. I only want to make a few comments in that these techniques are highly iterative, very ad hoc, and give absolutely no information about what the limits of the method might be. Okay, so in this new work with James, we're taking a much more systematic approach. We're going to replace iterative processes by a direct approach, a direct process that will, in a sense, deploy all the type 1 and type 2 information all at once rather than piecemeal. And this procedure, in principle, allows us to evaluate these constants, or at least to approximate it to any degree of accuracy with a finite procedure. Okay? Not claiming yet that that finite procedure is practical, but I'll show you the basic setup that we're going to be using. Okay, so the one thing I can report is the following. I'm going to define a integer m by 1 minus gamma is between 1 over m plus 1 and 1 over m. And then the asymptotic holds if and only if either gamma plus nu is at least 1 or gamma plus nu is less than 1, and 2 other conditions, which look kind of funny, but they come out naturally from the method, from the ideas. Talk about, oh, that should be 1. We'll talk about where these come from shortly. Okay. So the bottom line is we have a complete theory of when we can have an asymptotic, or when we're guaranteed an asymptotic, and when we are not guaranteed an asymptotic.
Wait, sorry, hypothesis A has 2 parts. One where you get the prime number theorem.
Oh, no, sorry. Yeah, hypothesis A. Sorry about that. It should be.
That should be there.
Yeah. Put a line under the second line. Yeah. There's a hypothesis and a definition, which is not part of it. Yeah. Sorry about that. Yeah. Now it's somewhat complicated. So let me go through some examples. I first wanted to talk about quick reduction.
This is a really Sieving limit. You're saying that if that's satisfied, then C is positive, and if it's not satisfied, it's 0.
No.
I'm confused.
I'm saying if this satisfied, we have the asymptotic. If it's not satisfied, there exists a sequence
Which
that fails the asymptotic.
Okay, got it.
Yes.
Okay, so it is really those 2 lines are very.
So at least from the point of view of if you get an asymptotic or not,
Okay.
it's a very easy to
Okay,
apply
complete story for the positive.
complete story, and these hypotheses are very quick to verify in practice. Yeah. So I wanted to make a couple of preliminary reductions. So we don't really need to consider all triples gamma, theta, nu. First, no reason to consider theta bigger than 1/2 for the reason that if you have the type 2, it sits in this range x to the theta plus nu. So if it works in this range, if and only if it works in the complementary range. So x to the 1 minus theta minus nu, x to the 1 minus theta. Simply by replacing a divisor with its complementary divisor. Sort of swapping the roles of m and n, essentially. Second, we can assume that gamma is not in the type 2 range. Now there's a kind of important that this be written as half open, half closed. I can also assume gamma does not lie in that. And the reason is that if the type 2 bound holds in a certain interval, then the type 1 bound holds in the same interval, because this is a much stronger condition. Yeah. So if gamma did lie inside here, that would imply that you actually have a higher distribution, so you can increase gamma. All right. So under these preliminary reductions, okay, I want to do this over here. I claim that if gamma is less than half, then C gamma, or okay, theta nu gamma, I'm not sure what order these are supposed to be in. I think that's right. The constant's 0. So these examples of gamma equals a half were right on the cusp.
Wow.
All right. Since the proof is short, I'll show you the proof.
Okay.
Okay, first, we find
Saying that gamma is less than a half, there's no level of distribution in the other one that's good enough for general sequence.
provided that we have this.
Okay.
So you could say, wait a minute, I have gamma equals a half, but I have type 2 everywhere. Well, that's not gamma equals half. That's failing this. That means you really have gamma bigger than a half. Okay. So there is a caveat that we have to take into consideration. So we can find an alpha such that alpha is between gamma and a half and not in the type 2 range. Okay, and this actually follows from part 2 over there, and part 1 and part 2. I'll just say it visually. So either, okay, because of part 2, either gamma is less than theta, which is less than a half, or gamma is bigger than theta plus nu, in which case we can take alpha anywhere between gamma and a half. And then from this, we'll take the following. All right, I claim that we can have a sequence that's 0 on primes. There'll be some constant for numbers that are products of 2 primes. The first one is close to x to the alpha. The second is close to x to the 1 minus alpha. Okay, so you can have some intervals here. And the C is going to be appropriate for the problem. And then Wn is 1 otherwise. So Wn minus 1 is going to be supported only on primes and products of 2 primes of a special form. And one can actually check, because alpha is bigger than gamma, the type 1, the only type 1 bound that is relevant is d equals 1. And we can simply adjust C to make it work. And the type 2 range is completely out of the picture because of that. So there's actually a very simple proof that gamma less than a half is never enough if that's genuinely the largest gamma that you've got available. Yeah. All right, so of course, what we're saying here is that without additional information, you're not guaranteed an asymptotic. There are additional hypotheses we might put on these and succeed.
So what does your theorem give when gamma is a half and the smallest, your theorem is too complicated to be.
Yes. Let me illustrate that. Yeah, let's illustrate
So what is C in this equal? What is the size of C? Example you gave.
C was chosen.
Oh, C
What
is,
scale is it?
C chosen so that the sum of Wn minus 1 is about 0. Just so that it has average value. So it satisfies the type 1 when d equals 1. All right, so what by this I mean, take an interval around alpha and take P1 between x to say alpha minus epsilon and alpha plus x to the alpha plus epsilon. So this is a rather substantial set of numbers. And there'll be some constant that will work there.
But C will be blowing up as gamma approaches 1/2, I guess. So we should think of
Yeah, that's right. That's right.
gamma.
That's right, yeah. There's no a priori upper bound on the weight sequence here. Exactly because there are situations we would like to apply it where A is a sparse set. And the way I've set it up, then Wn would be either 0 or something really big, possibly even a function of x or power of x. Yeah. Yeah, so I had an example. Yeah, so let's look at this example. Where gamma is a half, theta is 0, nu equals 1/3. Okay, so let's apply this. We don't have condition A, that fails. Let's look at condition B. Here m is 2. And we'll look at B1. So the only relevant n is 3. So we only look at n equals 3. And you can see that the point 1/3 lies in the type 2 range. So 1/3 lies in. Okay, so B1 is checked. B2, well, 1 minus gamma is a half. 1 minus gamma is 1. That lies in the complementary range. So for this particular set of parameters, you just go through it carefully. It's very simple. And for all the cases that we know that have been applied, it's very easy to verify by hand. There are some choices. Let's say if capital M was 1,000,000, where you might have to use a short computer to verify this, but it's a very simple finite process. So this essentially, and even though it follows from our theorem, in this particular case, I'll attribute this to Duke, Friedlander, and Urbana. Now we can consider the one parameter family. So same theta, same gamma, but now nu is somewhere between 0 and 1/2. We know at 1/3 we have an asymptotic, and you can check that if nu drops below 1/3, it's gone, no asymptotic. Yeah. So in the range 1/5 to 1/3, this is in new work with James. We have an exact value of C. We can express it exactly. In particular, at 1/5, it's about 0.362. And by contrast, Duke, Friedlander, and Ivanitz in their paper got a lower bound here, which was about 0.23. So it shows that already there was some inefficiency there. Although with our setup, this was actually pretty easy. So in a slightly lower range, 0.1, a little bit above a 6 to 1/5, we have that this constant is positive. We have some way of showing that, and we believe our method is optimal in this case, in which case the threshold we conjecture should be close to this. We haven't quite proved that yet. But we've shown that if nu is a little bit less than that, then in fact, this via a construction, the constant is 0. So this is relevant to Peter's paper, where the 1/5 came from a conditional construction. Unconditionally, they showed that nu was, I think, 3/19, which is below this.
Yeah, well, that's.
So with
But
yeah,
what was funny is I told him we were using approximations to Ramanujan, and I said, we have such good approximations that this can't be the issue. And it, of course, was. We landed at below. I mean, we didn't know it was 0. We didn't know you had.
right. It was actually, this was posed as a question in Duke Freelander and Ivanus's paper. They suspected that it was 0 at some point, but they asked just to find what that point was. Yeah. So I want to talk a little bit about another one parameter family. Yes, I can. And this is what we actually we got started with in the paper.
Are your examples still products of 2 points?
Oh, here?
Yeah.
No, it's much more complicated. It involves interaction between integers, but between 1 and 5 prime factors. Okay, but we have a system for creating these constructions, and I hope to show you at least one kind of baby example of that a little bit later. Exactly for this one parameter family here. And this one parameter family has arisen when people have been studying fractional parts of alpha p, where p is prime and alpha is a given irrational number. So if I let C tilde of theta to be C theta, the constant in this case, we have a theorem where we have the exact value. I'm not going to write it down, but in the range 1/4 to 3/10. And in particular, at 3/10, our value is about 0.844. Now, Harman, in his book and papers, has worked very hard on this problem. And in this particular case, we have an exact value. Harman was still doing things inefficiently. Somewhat. I mean, so again, this illustrates some of the power of our new methods.
Explain how you can get any exact value from some functional.
That's what I'm going to try to explain in the last part of the talk. Yes. Yeah, how can that possibly be? So the starting point will be something called Linux identity. I alluded to it earlier, which is almost an identity for indicator function of primes, and it's, I'll call this T of n. If you haven't seen it before, it looks a little funny. But if you write down the Dirichlet series for the left and right sides, a little manipulation will show you that it's the truth. We're also going to need a truncated version of this, where we have the same, basically the same, except the DIs are now limited to being at most one. Okay. So I have to move the asymptotic for a moment. Okay, so I'm going to be skipping a lot of details here, but this is essentially what we're doing. The first step I just explained. Okay, so I replace the variable p with n, and I put Tn, as now it's capturing primes. Now I'm going to deploy the type 1 and type 2 information. When we deploy the type 1 information, this essentially allows us to replace Ty of n, T of n with its truncation. So any DIs that are bigger than y, we can take care of those with type 1. Second step is to deploy the type 2 information. And what this allows us to do is essentially remove from consideration any integers that have a divisor in this range. So the set U is the set of n up to x, no prime factor less than or equal to y. Okay, so Ty of n is actually supported now on what are called y smooth numbers, integers without any prime factor less than y. So that's where that comes from, and also no divisor in okay, I should put it in terms of x in this type 2 range. So again, I'm leaving out a lot of detail, but once you have this, a couple of observations. If the set U is empty or infinitesimally small, then we obtain the asymptotic we want. Okay, so that's how we prove 1/2 of the theorem that I just erased. Now, it begs the question, okay, if we don't expect an asymptotic, and we now know when we can and can't have that, how can we use this to bound the constant? Okay, well, by itself, it's not enough. We need some more, a little bit better analysis. And to explain that, I first want to mention that in a lot of this work, and this is true for other people as well who worked on these things, we're going to map an integer n to a vector Vn, which captures the relative size of the prime factors. Okay, so this is a vector whose entries have sum equal to 1, and they capture how large these prime factors are. All right, so it's going to get a little technical, but so WSL will be the sum of integers up to X, no divisor in, okay, I'm going to call this B. Okay, this will be the, okay, B for bilinear, so that's the type 2 range. L prime factors bigger than Y, S prime factors less than Y. Okay, so there's going to be this cutoff Y, which is X to the 1 minus gamma. That's related to the type 1 bound. So we're just giving some notation to integers with a certain number of large and small prime factors. This is related in the vector world to a quantity I'll call QSL, which is vectors with some 1. And let's say there are S small ones and L large ones. And this divisor condition translates into no subset sum in the interval theta plus nu. Now, this subset sum condition can be very, very complicated. Each of these basically is cutting a hole in your region until it looks like multi-dimensional Swiss cheese. So in particular, performing an integration over this region would be computationally very hard to do. Okay, so now, as long as L plus S is at least 2, that means we're not looking at primes. I'm going to define or let H of SL be a function on 2SL, which is non-negative, and I might as well assume it's piecewise smooth. Then let's go through the following calculation. Okay, what have I done here? I've encoded the fact that Wn is greater than or equal to 0. That's it. But only on certain numbers with certain weights. This idea, by the way, it was motivated from the duality principle in linear programming. So now using this idea, but not applied to a prime, but applied to all the large prime factors of n, produces a giant sum over numbers n, where I have S prime factors, and now L other factors where the QIs are no longer required to be prime. We have these Linux factors. And now this function evaluated at the vector of the log pi over n's and the log and these others as well. Okay, so these last vectors don't correspond necessarily to primes. For a given number n, there are many ways of representing n in this form. You can combine prime factors in many different ways to make these QIs. Even the S and L are not fixed. So just as a crutch, I'm going to let Tn be the accumulated factor that comes in front of n. Okay, and this can be computed explicitly in terms of the h functions and these Linux factors. Okay. So what? Now comes the perhaps the most crucial part of the argument. Oh, okay. Actually, I want to make this a function of the vector, but it's essentially the same. Suppose that this complicated combinatorial factor is equal to the Linux function at n for n in the set U, defined over there. Then, what is this right side? The right-hand side is which, when we compare with what we had written on the left-hand board, this is asymptotic to the sum that we wanted in the first place, the sum over primes. Okay, so now this is asymptotic to this, to this, to this, greater than or equal to that. And what we have obtained is a lower bound for the contribution on primes. And these HSL functions are arbitrary, subject to condition star. Okay, so now the name of the game, optimize the choice of HSL subject to star. Okay, now the way I've written this, it looks horribly complicated, but in certain situations, combinatorics is simple, and I'm going to show you one example. Also, if we have, let's say, a set of functions HSL which we think are optimal, how would we prove that they're optimal? Well, this calculation here, if I add this piece over here all together, this calculation shows when it's optimal. It's optimal when this inequality is in fact an equal sign. In other words, if we can construct a weight function for which we have equal sign, but that means that Wn has to equal 0 on the support of these HSL functions. So that gives us a target. So if we can actually construct a weight sequence, which is 0 on the support of these guys, we will then have proved that this holds with equality in some example, and we've then proved the exact value of the constant, which would come from evaluating this, which can be done using multiple integrals. Right.
How big is K when you're doing all this? It's going to get, I mean,
Okay, I don't know what you mean by K.
N is a product of K primes, and you're putting this into this analysis. When you said K was 5, in some examples, is K 5, for example?
Okay, there are a big class of problems where K is limited by 1 over nu.
Yeah, okay, so it depends on the parameter.
Yeah, so if nu, which is the governs the length of the type 2 interval, if that is very tiny,
then that
the
could be
problem
fine.
is much more
I'm
complicated.
just saying, given the parameters, then there's some K is limited by the parameter
Yes.
Okay, that's what I want.
So in principle,
Linux.
for examples, in practice, there are only a finite set of SLs in play.
Okay.
So let me illustrate that. With this example, so this will be my final part of my talk. Show that this is practical. Okay, so this will be a subset of the range I defined earlier. Now, in place of U, I'm going to define the set U star, which is the set of values where the Linux factor is non-zero, because they play no role in the argument. In this particular case, this is very easy to see. These are products of 4 primes, I guess, that are around size X, and the primes lie between X to the nu and X to the theta. So in this case, U is very simple, and moreover, in U star, the Linux factor is constant -6. So then star becomes the following. So I'll think, so now T is a function of a vector of 4 quantities whose sum is equal to 1. This has several pieces. So the only pieces in play is H02. There's H11. And H40 comes by itself. And then the critical part. So that's what the T function looks like. Notice that our target is -6, and the little h's are non-negative. So little h02, 1, 1, 2, 1, and 4, 0 have positive coefficients. So they're pushing in the wrong direction. So it turns out that the optimal choice is to just take those to be identically 0. And the one that's negative, well, there's actually an obvious choice that works. There are 4 variables, therefore there are 6 summands. So if I just take H21 to be identically 1, boom, we're done. But that is a very inefficient choice. So H21 identically 1 works, but inefficient. The best choice to take. Now I'm going to use different letters here. Let me explain this. So these are the 2 small variables. This is the large variable that's indicated by the subscripts. Twice the indicator function that the 2 small ones have the sum at least a half. Now, why does that work? Well, given any 4 tuple of positive numbers that sum to 1, exactly half of the pairs will have sum at least a half. Because every pair and its complementary pair, exactly one of them will work. Now, why is this better? It comes from evaluating this. Right? This particular example here took us months and months and months to figure out.
Not a linear program.
No. There was a kind of new symmetry that we discovered between the interaction between these numbers that have products of two big primes, that is the 0, 2, and the products of 4 primes. So there was a kind of a new interaction going on there. Now, I said these were optimal. So on the construction side of things, how would we prove it? Well, we need Wn to be 0 when n is the product of 3 primes, and P1 and P2 are less than y, and their product is bigger than square x, and P3 is bigger than y. Okay, that's the corresponding part of this, of the support of this function, translated into from vectors to integers. Now, to do that, that was also a difficult part, because the type 1 information puts constraints on the interaction of these different types of integers. Okay, so the only types of integers in play are the ones you see here. 4 small, 2 large, 1 small, or 2 large and 1 small. Or sorry, 2 small and 1 large. I know I'm running out of time. I was going to write down the actual integral equation that needed to be solved, but there is an integral equation that we had to solve. And to do that, we had to go into an excursion into the theory of Volterra integral equations.
Linear?
What?
It's a linear equation or not?
No, highly nonlinear. We could not write down an explicit solution. We just had to use the fact that it was existed and it was unique, and then get some bounds on it. Yeah. So, if anyone's interested, I could spend 5 minutes writing down that part, but I think I'll stop here.
When Ben Green was lecturing here some years ago, in paper 2, Tau,
Yeah.
came to Martin and said, why is there no sublimit for type 1 and type 2 sums in the literature? Okay,
Yeah.
you had to wait a while. Now, this is beautiful. I think it really, it's remarkable way to get exact answers. Because I forget, in the type 1 sum, it's quite an involved,
Yeah.
right? Not all sublimits are known, right? I mean,
No, I think for dimension half and 1, that's it.
that's it.
But this is all dimension 1.
Yeah. Like I said, we've been working on this project for 5 years, meeting in various places. We still don't have a preprint because every little step has come with a great deal of pain. I mean, this took, long time to come up with. Working the construction was another long time, and that's just one little example. And then, we started working on with other intervals, and other issues started coming up. So it's been a really interesting project where we're off in uncharted territory. So yeah.
Can you determine, like, fully characterize when C is positive if you're given?
Oh, that would be the dream. That's the dream, is have,
So do you
say in this region it's positive, outside it's 0. One of the things we don't know, let's see, in this case, when theta we understand very well what happens between 1/4 and 3/7, sorry, 3/10. When theta gets close to 1/3, the type 1 information approaches 2/3, the type 2 gets really tiny. We think that the constant becomes 0 at some point. And we've worked out an extremely complicated example that we think shows that, but it depends on a tremendous amount of numerical integration over complicated regions, and we don't feel that it's fit for public consumption at the moment. Yeah, so there's just one example where we're not quite sure what's going on.
More questions? Any questions from Zoom? No. All right, if there are no more questions, let's thank Kevin again.